introduce to you today Dr. Aijun Song, who is an assistant professor in the Department of Electrical and Computer Engineering. We have a lot in common with him because he's interested in developing underwater acoustic devices that we can use to do some exploration in coastal areas. He had done already some of it, and so he's going to talk today about his projects. Recently he got a few NSF projects funded, so it's a pleasure to introduce him today.
Thank you, Natasha. It's my pleasure to kind of share some research with you all. I have the first observation. You guys are the hardcore water group, right? And I also have a couple comments about myself. First of all, I teach in the electrical and computer engineering. It's kind of a little bit far from your field. This is the first thing. Second thing is, here I talk a lot of things. I got talk about robotics. I talk about sampling. Really, to be honest, I only know about one particular thing, which is like a narrow field on my research. It's about underwater wireless communication. So the third is that Natasha probably kind of hinted that the talk, some of it is about the future. So it's not like I have done it all. So it's like ongoing part of it. I did some part, and some part is more about future. So for that reason, I want to make it more kind of conversational. Stop anywhere you have question or you have some kind of doubt about my assertion here and there. So a topic it is really the direction I'm heading to is about underwater acoustic networks for mobile platform. The mobile platform, the majority of this is this guy is an autonomous underwater vehicle. Okay, I believe some of you know this better than me. So this is where I'm referring to. I'm not really an expert on this. I'm a user too, but I know that AUV started being adopted in oceanography, marine science in 1990s, right? And now is the third or fourth decade almost. And there's really a wide interest from oceanography, marine science communities to use this because it's cost effective, right? That's the thing. You can get data at cheap price. You can, of course, that's a comparison compared to ship-based sampling. Also, U.S. Navy is very interested in this because this guy is also very effective for warfare. Right? He can do surveillance, you can do national security, you can do a lot of things, very good, very robust in dangerous location, in extreme environment. Okay, so from these two applications, basically NSF and U.S. Navy are both interested in investment. Okay, and as I said, I don't do this robotics myself from by training. My training is in the communication. I started to use the AUV about 2 years ago, and one of my collaborators has an eco mapper. He said, "Do you want one?" I said, "Sure, yeah, okay." He basically kind of gave it to me. We sometimes collaboratively use. I mean, that's joint use. Let's put it this way. So my students were excited, and we say, "Yeah, we need to put this to use." But before anything, I told them, "Okay, this guy is really expensive. 100,000 K. It's 100 thousand, right, dollars, and they start getting nervous. What if I got lost? Yeah, that would be serious because this doesn't belong to me per se. Audition is a lot of money to me. So they say, okay, let's come up plan, safest plan possible. Okay, and so first we can test it in a small lake. Yeah, I said that's a good idea. Right? Let's do that. And what if it goes down, there's comes back? And then it came up, the solution said, yeah, let's first drive this guy on the surface. That's good. And what if it sinks? We can put a little float, right? Attached to it. And they came up to say, what if it gets into the middle of the lake, we cannot get it? And they say, oh, we can use a little boat to follow it. That's what they did. So I can play a little video. That's really the first encounter for us to use the AUV. So it's pretty pleasant actually. That experience. They were on a lake. The weather was not very harsh. It's actually 2 years ago, the Chinese New Year's Day, Chinese New Year. Okay. Yeah, my students are very good. I cannot complain much. So in the morning they did everything. It was perfect. Afternoon, the wind picked up, and the strong wind pushed this guy to the other side of the lake. They fight the wind. They cannot get it back. They cannot get it back. In the end, they have to abandon the boat. They have to, because the other side of the lake, there's no access. They have to find a way through forest. Because they need to retrieve this guy, and they fight. They didn't have anything to eat for like 8 hours, and was on the foot, trying to get away, kind of get back. And it was a kind of tremendous struggle, and probably the whole day they spent 10 hours in the field. Finally, they got back and they took the AUV back. But that's the kind of first story, and it's getting better from there. Couldn't be more words, but. We practice after that. We practice a lot with this vehicle, and there's some incident here and there, but we are very lucky we didn't lost it. And so to the point we gain our confidence. Said let's do experiments in the Lake of Tuscaloosa. There we kind of struggle a little bit, say if we need to do it or not, because it's a bigger risk, right? And I can show the video here. Right? You see the vehicle goes in and dive in and disappear. Okay. But the purpose of this is more like it's an exercise. I admit that, but also we want to do something to collect data. Because I study acoustics, so I'm interested in marrying acoustic data, acoustic intensity. And we're also interested in the ambient noise, the two kind of parameters. Now, this is what we did. We attach a receiver, the acoustic recorder, to this guy. So basically duct tape it. With zip ties. That's kind of very simple way. And that's the vehicle side, the receiver side, right? And a transmitter, we found a very nice docking area, the deck, and we hand down a transducer transmitting sound into Lake of Tuscaloosa. So after this setup, we basically program the AUV, right? Make a mission, right? And you'll see the tracks next page, and then we release the AUV. The AUV, when it's in the water, we transmit, so it hears the sound as it surveyed, it goes through the area. Okay. So it's like this. So this is where the transmitter is. The vehicle just go like, see, this kind of vision. Right. I believe this is 2 missions. Okay. And they are, so this is the other one. And make the swimmer like a grid, right? Because this vehicle has a depth sounder, has a altimeter, so you can easily measure the bathymetry. Yeah, this is the bathymetric results. So I have a question. How deep do you think is the Lake Tuscaloosa? No.
Just in the center of the lake?
It's 28 meters maximum.
Yeah, but we didn't go far. I believe it's up to probably, in the record, probably 50 meters, even 60 meters, 60 to 70 meters, and the deepest point. But at least 40. I mean, that's easy. I think it's going easy because we still to the furthest point. This is the kind of the deck, right? And this range is only 300 or 500 meters maximum. So it's not even a kilometer away. So I believe this is the further away is more deep. So it's probably 40 meters. You can easily get 40 meters.
So how deep was the vehicle all the time? Like it
Oh,
was
this
submerged?
is like 10-meter water depth.
So this is probably the optimum depth to get the signal, right?
Yeah, because before we doing this thing, we were down here. We didn't know how deep it is. We know it's pretty deep somewhere, but we don't know how deep was it. So we kind of say, let's put it more conservative. Let's do 10 meter, right? We don't want to do anything stupid, and that kind of. So we said 10 meter below the surface.
Okay.
Yeah.
But does it, okay, so question, if you do this in seawater, probably because of the differences in densities, you would have to adjust the depth in order to get optimum signal? Does the density of water, affect the receiving signal?
Yeah, definitely. So basically, this is an exercise for signal processing,
Okay.
and it's really at our decision what depths we're swimming at, right? You can do 10 meter if the depth is allowed. You can do 20 meter. In the ocean, it's same. If it's you can choose. You can choose if the depth of the ocean allows.
Okay.
Yeah. So you basically adjust.
Okay.
That's the. So that's the symmetry plot, and this is actually a very relatively small region. It's like, see, 350.
So how long did it take to take this data?
Yeah, that's a very good question. So the student programming it, the AUV reports back, say the program reports back 40 minutes. Okay, yeah, they said 40 minutes. That's pretty fast. One of the track, right? 40 minutes.
One way.
Yeah, just one of the pattern.
Oh, okay.
Come back to 40 minutes.
Okay.
Yeah, pretty good. And we say, okay, yeah, we just release it, and we were waiting. We were happy because this seems, working and went well. And 40 minutes, there's no sign of it. We start like getting nervous. I asked students, are you sure it's 40? Yeah, this program says 40. And she's kind of try to comfort my worry, say, probably there's some kind of current, give it an extra 20 minutes. Okay, yeah. Another 20 minutes, no sign of it. We were searching basically, we just asked the student, just pick a direction, just look for it. No sign of it. And another 20 minutes it came back. We just applauding. It was, oh, wow, come back.
So does the vehicle have like a radial sonar system, or is it just in one axis? So is it just looking straight down, or
Yeah, that's
just for the pitch?
Yeah, that's very good comments. So this vehicle has depth sounder, so it's looking downward, and it has a module you can communicate, but it doesn't work very well and takes effort to put it on. So we kind of not doing that. So if my answer is that this one only has a downward looking acoustic.
So then how do you know your depth, your water depth? How
Yeah,
far you're
yeah,
swimming?
yeah. And it can record because we attach a recorder, acoustic recorder. And there's no horizontal emission of any kind. Okay. Yeah. So that's the.
How much does the instrument weigh? The weight of the instrument?
The weight is about two grad students can lift it. So it's, yeah. Yeah. So it's like 80 pounds, 70 pounds, 80 pounds. It's pretty heavy. Yeah, pretty heavy. And the operation-wise, it's not that difficult. It's you just before in a lab, you just check the seal, just pump air in it, check the seal, and at the side, students kind of do the weight balancing, and then a couple of test rounds, come back, and then do the mission. At each of the elements, each of the small steps, we made a mistake, which is a good thing, I think. Now we know the whole procedure pretty well. There's a little story of that. One time, we were in a Lake Nicole. It's pretty kind of narrow, right? It's very quiet, very nice little lake, and we did exactly as we planned it. We test the seal before we go in. We charge the battery, and we at the side we did the balancing. We were careful. The students did a test mission. Go and come back. We said, okay, very easy. Okay, and I said, okay, good. You guys are very good at it. Let me get some lunch for you and just stay here. And I went to nearby restaurant and come back. There's no vehicle at the water. There's no students there. What's going on? What happened is that the test run was okay, but in the actual run, the vehicle was supposed to go to on mission and come back to the home park position. They forget to program to come back at a park position, the home position. So when I was away, they watched the vehicle, go through the mission and the surface and the middle of the lake. What's worse was that there's a little current took the vehicle downstreams, and they were holding the remote control, cannot reach it, and they were chasing the vehicle on land. But fortunately, Lake Nicole is not big, and it worked fine. But in the end, they got it. So yeah, it's been very fun for us. It's very exciting, very fun. And this is the measured acoustic intensity. So you can imagine around here is the acoustic transmitter, and of course this is the kind of location where you are close to transmitter. Here you're far away, so this is the reception is stronger here, and reception is weaker here. But one of the acoustics that you have this general trend, but you have a lot of variability as you go out of range because the nature of acoustic transmission. Okay, and what essentially to this point we say, okay, good, we get good acoustic data. Can we do something about it? The first thing we come up is that we can do interpolation, right? Interpolation, you have the measurements, this like a grid. You have basically have the measurement at this grid, and you can do linear interpolation. You can do the Kriged method. The third method is the compressed sensing. That's like a lot of us want to use that. The compressed sensing is especially good because you are guessing a pattern of your acoustic reception. That pattern in the transfer domain, you only need a couple of parameters. So basically, you use these kind of measurements to estimate a couple primary parameters. So a lot of time it works. And the Kriged, of course, you guys work with Kriged sometimes, right? Right. So that's pretty effective too. It's at a lower sampling ratio. It works very fine. But the grad students who work on this was trying to publish something kind of new. She came up with this strategy. So okay, we can do Kriged, right? We can do compressed sensing, right? And what about combine these two? The idea is pretty simple, and I believe some people have done it. But for underwater acoustic, nobody have done it. So basically, if you can do Kriged, right? From the samples we have, you can interpret for this whole picture, right? And her idea is that, okay, I have some real samples just on the grid, and I have some kind of virtual samples from Kriged. So how about I combine these two using the compressed sensing strategy to interpolate. Okay? Yeah, it's worked to some degree, but there's an issue because the Kriged method, the field, the Kriged sample, right, is also obtained from the real sample. And the Kriged, the virtual samples, it's not 100% correct, right? It's what you asked me. And there's certain uncertainty of your accuracy there. So when you put more samples there, the more virtual samples there, sometimes you are hurting yourself. And she came up with a strategy then. So okay, I can put a weight, right, to the samples, either real sample or virtual samples. Real sample, I say the weight is 1. I kind of firmly believe the actual sample, right? And if I have sample estimated from the Kriged, because from the Kriged I know that uncertainty. I say from there I can put lower weights to the virtual samples, and the lower weights is generally corresponding to the estimation uncertainty, right? If you have higher uncertainty, I give you lower weights. If you have least uncertainty, I give you higher weights. So then it worked pretty well. And so this is kind of results, and this is the measurements, and this is the interpretation results. And still, there's not perfect, but from the acoustic simulation, you probably can get something similar like this. There's not perfect, let's say. This shouldn't be there that strong, but something like this big strike pattern, and we see it all in acoustics. And she also kind of compare the weighted, she called it KCS method, compared with Kriged here, compare with interpolation here, compare with compressed sensing here, and you have better results. So let's come back to the basic of this plot. This is this axis is called sampling rate. So basically, when we do experiments, right, we have samples in this grid, but we don't have sample inside each grid, right? We have this line, right? If we assume a resolution we wanted, right, then we basically have a sampling rate. It's about 10%. That's the kind of assumption, right? That's where you see these three interpolation results at sampling rate 10%. Okay. The y-axis is called peak SMR, peak signal to noise ratio. Basically, probably Jacob can chip in, is a measure of how good you recover an image, right? All right, it's very popular metric, right? It's defined as dB, right? Is the ratio between maximum signal power and your average estimation error in our case. So the higher is the better, right? You can see Kriged is pretty good. It's around at 10% of sampling rate. It's much better than linear interpretation. It is better than the regular compressed sensing, and it's about 40.5 dB peak SMR. Okay, that's the these three guys. Okay, remember in the KCS, like Kriged compressed sensing, the student's method, right? He added virtual samples in, so you can actually increase your sampling rate. This is not a real sampling rate. It's like a virtual sampling rate. And when you add more sampling rates, and you can add it up to 90% of the sample, you get to 90% of the sampling rates, you actually doing like 3 to 4 dB better than Kriged alone. Okay, so yeah, we are pretty happy about this. So that's one of the results. So what happened is we kind of learned in sometimes dramatic way how to operate the AUVs, and we use the AV in the Lake Tuscaloosa. We collect the acoustic measurements, and we kind of do some interpolation, right? That's what we do.
I have a question. So I might have gotten this wrong. So let's say you have X number of sampling points, and you add virtual sampling points in addition to the X.
Yeah.
How, and you determine the uncertainty of it, and based on the uncertainty, you add weights.
Yeah.
How did you determine the uncertainty without calibrating the virtual points?
Oh.
Wouldn't it be easier to use 80% of the already sampled points and then put in virtual sample points where the 20% lie, use a Kriged model, calibrate the Kriged model, and then to test that model? Because
Yeah, I know what you're saying. You basically from Kriged method, you can get the uncertainty when you do estimation. That's come with your Kriged. You know, you can get the estimation MSE, mean squared error. Right, Natasha? Right?
What?
Yeah. Yeah.
I wasn't paying attention.
Okay, yeah, but you can basically it's pretty much like, so you have like a 10% sample, right? You estimate a few, you can predict, just as you said, you don't know a portion of samples, you can calibrate that. You also get it from the equation, Kriged equation, the uncertainty. So the uncertainty you can get that from the algorithm, Kriged algorithm itself, right? And for this guy, right? How do we measure the peak SNR ratio? Is that we have 10% sample, right? We kind of save 10% of the 10%. We just pretend we don't know the 10%. Random sample, right? And we do all this interpretation. We then use the results, compare the 10% of 10% we pretend we didn't know. We say, oh, that's the metric peak SNR ratio, okay, for each algorithm. So, and we rotate the pretended 10% of 10% throughout the ensemble of measurements we get. Okay.
So I have a different question. So you're doing this with acoustics, right?
Yeah.
With acoustic data. But you can use other parameters.
Yeah,
Any
exactly.
other-
Yeah, yeah.
So-
Yeah, because the compressed sensing, basically you are selecting a set of basis functions. I see Jacob is nodding. He's an expert on that. So, and for acoustic, we use a set of the basic function called contour net, right? You have wavelet, you have, curvelet, a lot of patterns. You just kind of have to see what your data, look for your data's pattern, and you match with your base function. So you basically use that, kind of match with data, and you convert your data to a transform domain. You just need to estimate a few parameters, ideally. Okay. So that's a single AUV, right? Single, and now we are trying to do this. We are trying to do multiple. As Natasha mentioned, that I have projects, we are purchasing more of AUV. So, and also this is a trend for environmental science, for oceanography, is that, one of AUV is very good. What about 5? What about 10? It must be better. Yes, that's the consensus. It will be better. You can imagine, because one vehicle, you get a grid, right? And now if you have 5 or 10, you basically, populate the area much easier, right, with samples, right? Not only that, if you have a fleet, and you can do, you can follow away the current front, you can follow the fish population, right? You can do a lot of the fancy stuff. And so that's why this is like, for marine robotics, for us, this is like a direction for research, like frontier, right?
So how many are you buying?
I buy two.
So totally 3
I think it's 2 or 3, so 4 probably.
total.
Yeah, total 4. Yeah.
Next question is how much you charge per time, per day to use that?
Yeah, we can work it out. Yeah, the students are cheap, you know. We can write joint proposals, right? Yeah, yeah, yeah.
Teasing you, but I think it's a real question.
Yeah, it is. But at the very beginning, we are trying to learn. I think,
Yeah.
and the MRI actually is intended for share use. So, the initial budget we budgeted for 3. We want to buy a surface vehicle. I think we probably will delay the surface vehicle. So within a year, I think I will get 2, and a little bit of that, if enough interest in the campus or nearby collaborator, I will buy all the 3. So I will have 4. Yeah.
Another question. I'm really interested in this. I'm sorry.
Mhm.
So, this acoustic waves, can they be used as a proxy to measure turbidity in a water column?
Turbidity, yeah, you can, this is called sensing, right? Everything underwater, you can use acoustic to sense. It's like RF for everything on land. You use radar to do detection, do everything, right? That's in everything underwater, turbidities, the salinity, the temperature structure, you all can get it out using acoustic sensors. But there's of course for example the current, right? The current speed, you can get that from ADCP. ADCP use acoustic, but turbidity, I don't know somebody did that anything with that. So it's no commercial product, right? So yeah, that's.
But we can attach turbidity meter to the vehicles.
Yeah,
You
yeah,
know, we
yeah.
can collect the data
Yeah,
that's,
yeah,
that
yeah,
way.
yeah, definitely,
You know,
yeah.
you can attach anything.
You
RSI,
can, if the sensor is compact enough,
yeah.
you can attach to the AUV. That's the sensing aspect. So there's really a motivation to use a fleet, but there's a challenging, because you can use a fleet as you want, but essentially you want this fleet, a vehicle just like fish school, or a dolphin school pod, right? They collaborate, right? And essentially you want this AV to collaborate, but how? You can use acoustics, but acoustic communication is extremely difficult. That's the part my research is working on. So, and we just imagine if we want to do it, we have a fleet AUV. We definitely need a couple surface vehicle to kind of construct an acoustic network to support the mission. Right?
Is there quite a bit of technology transfer from military to like your applications? Because I mean, I know that like with the South China Sea, it seems like they were doing this to locate flights, right, that have gone down.
Yeah,
Is that the same
yeah,
kind of-
yeah. That's the other part. But I'm referring to how this guy communicate with this guy, how this guy communicate with this guy. The acoustic definitely can be used to search object, mapping the seafloor. There's commercial product out there. There are commercial products for communication underwater, but they're not green enough. They are far away from green enough. So that's my research is about.
So the other question is, you can actually, if you have more than one vehicle, you can do depth profiles.
Yeah,
You can
yeah.
organize them
Yeah.
in vertical profiles, not
Yeah.
only lateral.
Yeah, Exactly.
Especially for
Yeah.
water certification in the
Yeah,
ocean, that's
definitely,
very important.
definitely. You're thinking about like Mobile Bay,
Yes.
the depth structure is very dynamic, it's very complicated, salinity change,
Yes.
dramatic, right?
Just to look at
Yeah.
the
Exactly,
certification with
yeah,
the
you
water.
can have multiple vehicles at the same time,
Yes,
right?
like in a vertical scale.
Yeah, I know what you're talking about. So you cannot do that with single vehicle.
Right.
And that's the so that's the kind of thing. Yeah. Yeah, question. So you know, that's kind of future looking is that I work in the acoustic communication and I buy stuff for AUV and also I work with a guy from Georgia Tech. The guy, he makes AUV, small AUV. So we can have more. And of course, his AUV cannot go to the ocean. It would be a swimming pool and small lakes. So essentially, we can kind of expand beyond beyond 4 vehicles. I know something about networking, but I also work the outside at a university, kind of do networking as a whole fleet. See, this is the Georgia Tech small EV, and we have done together integrated acoustic modem there. So this is being done. This is the vehicle I'm purchasing. I already placed the order for the acoustic module. This is all commercial, and this allow us to modify. So this is open access. You can take everything out. Hardware, software. You can change the code, C++. And here you use C to change inside out too. So that's the very good platform we will use. So you use this, and that I already placed order for 3 of these. And this is in the spring I get first one. So.
And like if you're monitoring, I don't know, migrations of animals and things like or whatever, can the acoustics themselves kind of impact that so that you don't really see maybe a natural process if the life forms are somehow responding to acoustics?
Right, exactly. There's some impact. There's some impact, but we are working at 30 kilohertz, which is to some population, like a dolphin, you are really have impact, but for a lot of fish population, it's not. I mean, I shouldn't. It's not, but generally it's not. But there are some kind of special case. But that's a very good question. And for those things, you have to do passive acoustics. You have to kind of hide yourself, just like if you want to stalk anybody. Of course, not a stalking. Stalking is not a good analogy. If you want to follow somebody, you just hide your footprint, right? Acoustic-wise, the same. You can do a little bit of that, and also you just passive. You don't emit anything, but you listen their footprint, acoustic footprint, right? So that's the yeah. And I also have right now 8 undergrad students to work on the surface vehicle. I mean, it's not a very serious project, but I just kind of ask them to play around, and then they kind of modify this to a motorized vehicle. Sometimes it's useful because you want this motorized vehicle when you have experiments. And I believe in the spring they can make it autonomous too. So that's those efforts. The rest of it, I kind of hesitate to show. I already out of time. The rest of it is the kind of the things I know. So it's acoustic communication. Acoustic communication is a very kind of hard problem. Navy has invested this like start from 1980s, and so far we haven't achieved the success you see in the smartphone. So a smartphone, like the first edition of smartphone is 2007, right? Right now, iPhone is like you call 10, iPhone 10. So there's many of improvements over 10 years. But for us, we haven't made much progress. That's the direction I've been working on. The main issue is that we have a sound transmission and sound reception of this kind of environments. We have reflection from seafloor, from sea surface. And that's basically is the non-echo, right? If you are in a auditorium room, if the engineer didn't make the acoustic right, and you basically cannot hear what the people on stage talking about. That's exact same issue. And it is like if you transmit one thing, you receive the direct copy, and you also receive the echoes. And of course, if you transmit, you speak one time, you cannot stop, right? The communication, you don't stop, right? You have another transmission. Another transmission has a direct copy and has the echo, right? And you don't stop, you have a third transmission, you have direct copy and the echo. And in the audience, right, this is what you transmit. You think it's pretty kind of clear, one waveform, the other waveform, and third waveforms. You know this is kind of separated. You know what's the true meaning of this waveform, but the audience, you know, very high reverberated environments, what they hear is the cluster of everything together. So that's the kind of fundamental question we are trying to solve. I kind of say we have to have equations. So if you have transmission, that's x of t, right? And this is your echo pattern, h of t. What you receive is the convolution of these two, right? H of t is the echo pattern. You want to cancel it out. We need to find a filter to apply so that the filter of g of t convoluted working only the h of t, you approach a delta. And basically, if you have that kind of filter, you apply to reception, you kind of have this whole thing as delta. Delta convolved with your transmission is your x of t, right? So that's what my research is about, to find good of g of t. Find good of g of t. Yeah. Yeah.
Last
Yeah.
question.
Yeah.
So for your vehicles, how difficult it is to put it on in a big river, or even a smaller river?
The only thing is the access to the river bank.
Okay.
If you have good access point, it's fine.
How about a fast flow river, like after storm or something?
I think there's a danger that the vehicle cannot maintain the mission. It's going to flood away, but other than that, that's because of the high current, right?
Yeah.
But if you be careful, you say, okay, first I would just like what we did, the vehicle stay on surface, it's visible to you, and it has an avoidance algorithm. So it has the obstacle it can avoid, and then it's fine. And of course, if you getting more comfortable, you can do different patterns, etc.
So if the vehicle lost the balance, what happens? Because you can still find the GPS location, right? Just
The
hovering
there's a different kind of issue. If it's flooded, that's your doom. It's flooded, you get synced. Then there's a chance of that. But other than that, as long as it's surface up, you get a GPS, it will try to fight it back to get it back. But from the fast flow, the current, probably the best strategy is that have a group upstream, have a group downstream, and start from small distance, and you kind of, you kind of extend the range you are trying to work with. Okay, yeah.
So what's the, so when you set up the track or the journey,
Mm.
what's the uncertainty in terms like a meter or even
The
to control I guess it's relative to velocity and current, right? So
Yeah,
do you have
yeah.
a estimated range, how far away can
Oh.
get away from the track, you said?
That's, we don't know yet, and it really depends on the current. It's
Okay.
different. We tell, in our environment, the current is probably half a meter per second. It's less than a meter per second, so we don't know others. It can get deviated pretty big. Yeah, that's the one of the things. Yeah. So. Yeah.
So I had two questions that kind
Mhm.
of go into each other. So in the first AUV example, you showed that you used a gridded pattern to
Mhm.
pathfind, if you will.
Mhm.
So do you see when you have a network of these AUVs that you might need to change that? Do you plan on researching different path exploration algorithms?
Yeah, that's a very good question. So that's the robotics, what they worry about it. But for now, I'm just assuming one AEV just do its own mission, do individual. There's another AEV just work on the other nearby location. They if they need to communicate, they can communicate. But yeah, I think people are working. Some people working on it with two vehicle. I don't need this one vehicle kind of do the grid pattern, right? I can use two vehicle kind of more quicker complete the survey, right? That's yeah.
I was wondering if the pattern or the algorithm that you would use would come into play with the communication issues as well.
Yeah, that's a really good question. You guys got good graduate students, and yeah, it's
I
really
think he's undergraduate.
depending on the location. That's why we do the acoustic field construction, right? You basically, if you have a transmitter, there's a sweet spots that dead zones, right? If you're in a dead zones, you cannot communicate. It's no matter how hard you do, if you use a sweet spot, you're doing better, of course, right? So that's definitely plays in the whole thing. Yeah. Yeah.
Any more questions? Thank you so much.
Sure, sure.
We
What do you mean,
really
just-
appreciate
Yeah.
you coming and
Thank you,
telling us
thank you.
more about this, and hopefully we'll have some results. and-
Yeah. I wanna see. I did some experiments in the Gulf of Mexico. This is acoustic stuff.
Okay.
Dolphin Island.
So who you are working with down in Dolphin Island?
Brian
Brian?
and Grant Lockridge.
Okay.
Yeah.
I know Brian, he's physical photographer.
Yeah. We were in the same university,
Oh,
University
okay.
of Delaware. So the first thing I came to Alabama, I contacted him. So I got good support from Diesel. So let me show one important slide.
Okay.
So I also have a indoor water tank. It's in the Cirque building. Okay. I'm recruiting PhDs. So if you are good math, if you are good at numerical modeling, it fits in my picture too. Thank you.
Thank you.
Thank you.
Thank you.